One thing that I think we can all agree on as TCG players is that giving your opponent extra card is generally, if not almost universally, a bad idea. But in the Pokemon TCG, that is an unavoidable hazard because of the Mulligan's rules, which reads, if you don't have any basic Pokemon, what do? First, reveal your hand to your opponent and shuffle your hand back into your deck. Then draw 7 more cards. If you still don't have any basic Pokemon, repeat. Each time your opponent shuffles their hand back into their deck because they had no basic Pokemon, you may draw an extra card. Which begs the question here. How many Mulligan is a given deck list expected to automatically provoke per game? Because that basically gives us the amount of cards a deck give on average to its opponent. Let's find out. Oh, and for the purpose of this video, Talonflame, well, the only playable Talonflame, will be treated as a basic because it's simpler that way. So let's start with a few definitions. For Big E, every possible starting hand for a given deck list. We have Big M, every starting hand that does trigger an automatic mulligan. Small m, the expected amount of mulligan per game for a given deck list. B, the amount of basic Pokemon or Talonflame included in the given deck list. D, the amount of card in the deck at a given event. Now, to have a hand that automatically triggers a mulligan, all 7 cards must not be basic cards. They can be any other kind of card from Energy, Special Energy, Stadium, Stage 2, Stage 1, Break, as long as it's not a basic. So the probability of having a hand that triggers a mulligan will be at each event the amount of cards left in the deck minus the amount of basic in the deck divided by the amounts of cards left in the deck. And thanks to the rules of Pokemon, since there's always 60 cards in a deck, unlike Yu-Gi-Oh! And Magic where you have a minimum and a maximum in Yu-Gi-Oh! In Pokemon it's exactly 60, which lets us simplify the formula to this here. This is your chance of getting a mulligan the first time, after shuffling the second time, after shuffling the third time, etc. etc. So if you want to know what's your chance of having a mulligan total, you want to know what's your chance of getting the mulligan a first time, plus your chance of having it a second time, plus your chance of getting it a third time, plus your chance of getting it a fourth time. The amount of total card you should expect from a mulligan will be the sum of the probability of getting a mulligan for n, x to the power n being all natural numbers. Now, that does lead to infinity, and infinity is a mess, and we will, rather than tackling infinity directly, we will find a roundabout way than dealing with infinity. I am not dealing with infinity on a video for a card game that is supposedly aimed at children. So one way of getting around infinity is to invoke the Judge Ball. The Judge Ball says that a Judge Ball triggers after n mulligan, where n is left up to the judge. A judge will search the deck until he finds the first basic Pokemon. The player then shuffles the deck, draws 6 cards, and the judge hands him the basic Pokemon that was searched as the 7th card of the player's starting hand. Now, if you're lucky, the place where you play Pokemon has a head judge which will give you the value of his Judge Ball. So where I play, it's 7. Thanks, Johan. So the equation we're going to work off with is this one here. The probabilistic amount of times you should mulligan with a given deck list is going to be equal your probability of having a mulligan power 1 plus your probability of having a mulligan power 2, plus your probability of having a mulligan power 3, plus dot 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 probability of having a mulligan power n, where n is the value of the judge ball. So let's take this given deck list by Xander Perot, who drove it to the semifinals of Vancouver Regional in October 2017. This deck plays 10 basic, and let's take the mentioned n value of 7. Now the probability of getting a mulligan for this deck is going to be .256, or roughly 26%. So if you're going to do this yourself, while I did approximate the first value of the equation to its 3 significant number, you have to be careful to actually use the full number of the third line and not simplify it during your calculation itself. I've shown it with the three significant number only to make it easier to see. Xander Perot's deck list has an expected average amount of 0.349 mulligan when the judge ball triggers at 7 mulligan. Another way of getting around the infinity problem is to find a value of n where if you have the probability of getting a mulligan to the power of n, you equal 0. Now, that is still infinity, but that's only if you use the mathematical 0. If you use a scientific 0, then you can get around that problem. And that's because unlike mathematics, where a 0 can be truly infinite, in science, a 0 always has value. Unless we're talking about a constant 0, which is rarely the case, 0 is almost never actually 0. It's going to be 0.00000 something at the end. So we just have to find a value which is small enough that we can consider it to be equal to 0. So let's take 1 in 1,000. So 1 in 1,000 in probabilistic term becomes 0.001. So if we use 0.001 as our scientific 0 for the equation, we get that probability of getting a mulligan power n equals 0.001, and that lets us calculate that the value of this n is the log of 0.001 divided by a log of the probability of getting n. Now let's go back to the example of Xander Perot's list. Now, we had the same first part, but now instead what we're going to do is we're going to find the n for this list. We plug it into the formula and it gets us that n is equal to 5.10792721616. Now, n belongs to big N, and big N is all natural numbers. So the biggest value that we have below 5.10792, etc., is 5. So the value of our n is 5. So if we use 5 as our value of n for the formula, we get that the probabilistic amount of expected mulligan is 0.348. So using this method, we calculate that Xander Perot's deck list has an expected amount of 0.348 mulligan when you approximate 0.001 as 0. The difference between the two approaches is less than 0.1%. Meaning, technically, yes, the value using the judge ball is going to be more accurate for a given event, but if you take a small enough number, using a scientific 0 will give you a close enough answer. But okay, now that you know how to get the expected amount of mulligan for a given deck list, How useful is this? Its first use is, of course, to be used as a simple tool to evaluate a deck. A deck that mulligans too much is a deck that gives you open too many cards. A secondary use of that is to compare the mulligan value of a deck list to another deck list, as either a tool of comparing which deck list has, at least in one aspect, a slightly superior statistic, or as in a way of knowing which deck, if they were matched up for a match, which deck should have on average more draws due to mulligan. How useful that is, I'm not really sure. Doesn't sound very useful. So, yeah, not that useful. But hey, it's fun to know. Originally today, I was supposed to do a video on the math of a turn 1 Lele supporter play. But the script for that video was many pages long. I estimated that it would take like a 50-minute video. It was ridiculous, especially since I could cut down each section in a video of its own, using other part of the games to showcase them, and then make later a final video where I just reference those other videos to make a clean, smaller video. So that is what you're gonna get next week. Next week, we're on the road to Lele Turn 1 plays. See you next week.